In this video, we're going to be looking at L'Hopital's rules. The rules are ways to find limits using derivatives. The rules you will see here are credited to the French mathematician with the last name L'Hopital. It looks kind of like the hospital. And it was actually first discovered by Johann Bernoulli, but accredited to L'Hopital, who later developed it fully. Let's do a preliminary investigation. Suppose I had 0 divided by 5. Well, we all know that the answer is 0. Suppose I said 5 divided by 0. Well, you would know that that is undefined. Does not exist. So if we take 0 and divide it by any number, it should always equal 0. And if we take any number divided by 0, it should not exist. But what happens if you get 0 over 0? Well, this is what we call indeterminate. Not yet determined. So if we took a limit and it gave us 0 over 0, we would need further investigation. Likewise, suppose I had infinity over 5. Well, that would still be infinity. Or if I had 5 over infinity, 5 divided by an infinite many, that would give us 0. So the next indeterminate form is infinity over infinity. So these are the two major indeterminate forms. We're going to look at some other really cool ones. But these are the two basics. I'm going to start off the lesson with these two basic indeterminate forms. So suppose we took the limit as x goes to some number c of the function f of x over g of x. And suppose that that led to the indeterminate form 0 over 0, or that led to the indeterminate form infinity over infinity. Well, what L'Hopital says here is that this limit as x goes to c is going to equal the limit as x goes to c of the derivative of the numerator over the derivative of the denominator. So it's not saying that f of x over g of x equals f prime over g prime, but it is saying that the limit as x goes to c of f over g is equal to the limit as x goes to c over f prime over g prime. So now let's do some examples. Example number 1. The limit as x goes to 0 cosine x plus 2x minus 1 all over 3x. This is not a limit that you probably know how to do at this point from pre-calculus. So let's take a look. The first thing we should do when trying to find a limit is plug in 0. Well, if I plug in 0, well, this value here is going to give me 1, and then plus 0 minus 1. So my numerator is going to be 0, but my denominator is also going to equal 0. Notice I didn't say that this limit equals 0 over 0. I simply denoted it with these brackets, telling the reader that I recognize that this is indeterminate. So now I'm going to employ L'Hopital's rule and take the limit as x goes to 0. Well, the derivative of the numerator is going to be negative sine x plus 2 over the derivative of the denominator, which is simply 3. This is not the quotient rule, it's derivative of top over derivative of bottom, not the quotient rule. Okay, so I'm ready now. I have the limit as x goes to 0 of a new function. I'm going to try to plug in 0 here, and it looks like I can, and the result of this is 2 over 3. So that is our limit. Let's take a look at example 2. Limit x goes to 0. Numerator e to the x plus e to the negative x minus 2 all over 1 minus cosine of 2x. So first step, try to plug in 0. Well, if I do that, let's see, it's going to be 1 plus 1. Take away 2 is 0, so my numerator is 0. And the denominator is 1 minus 1, so that's also 0. Good. So I have 0 over 0. Now this limit is going to equal the limit as x goes to 0, derivative over derivative. So this is going to be e to the x minus e to the negative x over the derivative of the bottom, which is going to give me 2 sine of 2x, as I employed the chain rule here. Okay, now let's plug in 0, and I've got 1 minus 1. Okay, so now the numerator is 0, and on the bottom 2 times 0. So look at that, we have again 0 over 0. So according to L'Hopital, I can take the derivatives again. So this is the limit as x goes to 0, derivative of the top, e to the x plus e to the negative x over the derivative of the bottom, and that's going to give me 4 sine cosine, like that. And now I'm going to try to plug in 0 again. This time when I plug in 0, the numerator becomes 1 plus 1. The numerator becomes 2, and the denominator is 4. So I'm just going to simplify that, and the limit goes to 1/2. Example 3. Limit as x approaches pi over 2 from the left. So this example will illustrate a couple things. One of the things it's going to illustrate is that L'Hopital's rule applies to one-sided limits. Alright, so we have to do a little bit of plugging in here. So I'm going to plug pi over 2 into tangent, and a working knowledge of some of these trigonometric functions is absolutely crucial. So let's come over here and take a look at the tangent function. We know something is special happening at pi over 2. So the tangent function will come down like this. Asymptotic behavior at pi over 2. Now if I continued to draw this, it would look like that. Okay, so we're looking at the function tangent of x as x approaches pi over 2 from the left. So we see that this is going to grow without bound. So the numerator is approaching positive infinity. And a quick look at the secant of x says as x approaches pi over 2 from the left, that is also going to grow without bound, so that's also positive infinity. So this gives us the indeterminate form, infinity over infinity. So you know what to do next. We're going to say this is equal to the limit as x approaches pi over 2 from the left, and I'm going to take the derivative of the top, and the derivative of the top is going to be 4 secant squared x, and the derivative of the bottom is going to be secant x tangent x, which brings us to the next thing this example illustrates. And you'll hear me say, hopefully several times, that if you can simplify, then you must simplify, and so we shall simplify. So in this problem, before I would plug anything in, I'm going to simplify what I can. So this is not L'Hopital's rule, what I'm doing here. This is just good old-fashioned simplification. I see I can cancel out one of the secant of x's. So it's going to be 4 secant x over tangent of x. Now this can simplify further still. And this simplifies to, again, this is not L'Hopital's rule yet. It was L'Hopital's rule here, but the next couple equal signs is just good old-fashioned equality through simplification. So secant is 1 over cosine, and then tangent is sine over cosine. So let's see, that's going to simplify to be 4 over the sine of x. Work that out, you'll see it works to 4 over sine of x. So now I'm at the phase where I can plug in, perhaps I can plug in, and so this limit is going to equal, well, 4 is 4, and if I plug pi over 2 into sine, that's going to give me 1. So the limit is equal to 4. Example 4. The limit as x goes to infinity. This is also a one-sided limit statement because we're approaching positive infinity or infinity from one side. So let's take a look. I have to the right here in blue the square root of x, and the orangish red is the natural log of x. In both cases, even though it doesn't look like it, in both cases each one of these functions grows without bound. So as x grows infinitely, the function ever so slightly will eventually grow without bound also. So this leads us to the indeterminate form, infinity over infinity. All right, let's do it. So this is going to be equal to the limit as x goes to infinity. And I'll stop for 1 second. I can't simplify here. If I could simplify, then I would simplify. So, and then I would have to simplify. Anyway, equals the limit as x goes to infinity. The derivative of the numerator is 1 over x. And the derivative of the denominator, we'll think of that x to the 1/2, so it's 1/2 x to the negative 1/2. I'm sorry, yes. So that's going to be 1 over 2 square root x. And it looks like I can simplify here. So again, this is not another L'Hopital equality, but this is just some, well, let's just rearrange this. So this is 1 over x times the reciprocal. So 2 times x to the 1/2 over x to the power of 1. I'll simplify that further. So this is the limit as x goes to infinity of 2 over the square root of x. Alright, so now the numerator is 2, but the bottom will grow without bound, and so this limit will equal 0. In example 5, it's the indeterminate form, infinity over infinity. E to the infinity will grow without bound, infinity squared grows without bound. So I'm going to employ L'Hopital's rule. X goes to infinity, making sure I couldn't have first simplified, which I can't. So this is going to be 3e to the 3x over 2x. Looks like, again, this is infinity over infinity. So I'll do it again. The limit as x goes to infinity, 9e to the 3x over 2. So the bottom stationary at 2, the top will grow without bound. So this limit doesn't exist. Specifically, it will grow without bound. I will say it approaches infinity. Most authors will say equals infinity. I'm a little bit queasy about that. You are permitted to say equals infinity, or simply write the arrow to indicate it is approaching infinity.